Hello and welcome to how to use Exotic in PTR SageMaker. So assume you've already got your SageMaker account and PTR SageMaker set up and you've done something, maybe not very much, but you know how to get into here. Now, doing an exoplanet transit is a bit more involved, slightly more involved to set up than a variable star or something like that. We need to first look at the data to figure out the coordinates of our system. So even before we use SageMaker, I'm going to go through and make sure that you get the right RA index for your images. So when you look up, today we're going to use HAT 23B, I think it's 23. I kept on using 32 before, I'm getting myself all confused. But if we go to the NASA Exoplanet Archive and HAT P23 overview, we'll use this actually, this page later on in more detail. And in the stellar parameters, where the star is, it'll have an RA and a deck. And it's tempting to take that RA and deck and use this one, but it's way better to use the ones from your own images, and they come out in the right kind of format as well. Okay, so how do we do this thing? So let's go into the Data Lab archive, and it is, at the moment, it's May of 2024. Some of you, it may be years in the past, but if you're still in May 2024, hello from yesterday. But to find it, we'll type in HAT into object, which will just show us objects that have HAT in them. And I think this is the only HAT object we've seen in the last week, so I'm pretty relaxed about some of the other options. But if you have to set the date, maybe if you watched it every night, you have to set the date for the night and the range and things, but you can play around that later on. But if you're looking for this test data that I'm showing you, here it is. And so if you go HAT, over that range, there it is, HAT P23B. So you see thumbnail, small JPEG, EVA, SecPhoto, psXphoto, JPEG, all sorts of different files. So we're going to use some of these photo files to actually measure the transit. The photo files contain our measurements of the stars in the image. And we'll need an actual image. We won't need all of the images, which is great because they're too big, but we'll need one at least. So we'll get one of each first, and we won't put it into SageMaker at the moment. We're going to use it on our local computer, and we're going to use our super duper general purpose tool, Aladdin. But first we need just an EVA file from the night. Doesn't matter where, doesn't matter when, just a single one, and a photo file. Well, PSX and SEK. So you might use two different files, and there's two different reasons why you would try one than the other. One works in better conditions, but if the other one works, it gives you better results. So we always try with PSX first, is my suggestion. So here we've collected the EVA, the PSX, and the SEK photo file. Now, if you're having trouble trying to find them, you can change the reduction level here, and it'll just show you EVA files, which is the image file, or it'll just show you PSX files, or it'll just show you SEK files, so you can limit this view like that. If you're looking for your data on a particular telescope, you can pick your telescope. But here, I'll just pick these three because they're right in front of me. So you need an image and the photo files for the types you're using. So get one of each. And then we'll go download, and it'll download to our computer. Takes a second. And then, depending on your computer, it's going to be all sorts of different ways of, it's free typing, doesn't it? Weird. Must be a link on my thing. But each computer will have its own way of opening up the zip file. Mine seems to be taking a moment. And here we are. So this is my computer's way of dealing with zip files, and I'll put it somewhere. I'm just dumping it on the desktop. You might have a better place to put it, more organized, but I'm just showing you this, so I'm just dumping it somewhere random. So we're going to, if you saw what I did there, I got the image and I dragged it into Aladdin. And Aladdin's great because here you go, here's the image. I'm rolling my mouse wheel in and out, and here I'm holding my right mouse button and moving around, and that allows you to change the brightness and contrast. That's not why we got the image. We got the image so that we can put our measurements on top. So we have PSX photo files which look like this. Just a bunch of numbers. RA index the position, so each one of these is a star at a position. It has it where it is in the image, and then how bright it is, basically, and how sure we are of the brightness, and then how sure are we of the position. So we just have a file of lots and lots of measurements of stars in the image, which is great because we don't have to measure them ourselves. So if we drag this into Aladdin, it will overlay those measurements on the actual image, which is great. If you zoom out, you can see why there's so many entries in that text file, because there's lots of stars. And this isn't even a big image. This is quite, well, compared to some of the cameras we have. Okay, so generally speaking, and this is not always true, but if you're looking at a quite bright star and you've observed it and put the coordinates of the star in as where you want the telescope to point, it's usually going to be a bright star pretty close to the center. Now, that's not always true. It could be you're looking at a dim exoplanet and it's over here. But you can check this against NASA Exoplanet Watch, which I suggest you do, because you don't want to go through all this and then find out you're looking at the wrong star. So you have the star here, and up here in the command area, the coordinates that are underneath the mouse are changing as I move my mouse around. So if I have a look, put it over here, and I go, it's 20, 24, 29. And that's also what's over here on a NASA exoplanet. So right, I'm pretty confident we've got the coordinate right in that dimension. And the other one's 16, 45, 43. And so, you know, close enough. So I'm pretty sure that it's this star. And magically, I didn't even intend this, it's already popped up and told me it's a planet. So it's figured that out from the image. That's why Aladdin is so good. So now you can be confident that this is your planet. So why did we do that anyhow? Now we know we've got a planet in the image that we're looking at, which is, of course, you knew that because you took the images. The important thing is we want to get the position of the star in our data set. Not from NASA Exoplanet Archive, and definitely not from anywhere else. The position that is in our images, because it can be different from what's online. Stars do move, not by much, but some do. Proxima Centauri moves quite a lot, for instance, which is something someone is looking at with our telescopes at the moment. So we want to record the position. So the RA and the DEC. So we want to have a piece of paper or a notepad here, and let's write down, double checking that you have the right numbers there, the RA and the DEC. And if it's a negative DEC, the sign is important, but this is a positive declination. So here we go. We've got the position of the star in our images. So that's good. Now we throw Aladdin away into the dustbin because we're finished, because that's all we wanted to do. We wanted to get the position of our exoplanet host star from the image itself. Okay, so I'm going to put this over here, out of sight, out of mind. Okay, so we've gotten nearly 10 minutes into this video and we haven't touched PTR Sagemaker once. So let's go in. Okay, so open a notebook. I prefer using notebooks. And you have your standard from ptr Sagemaker, import ptr Sagemaker. Now, if you haven't updated it for a while, if you've just installed it and this is your first time, then you don't have to worry about this. But if you haven't updated it for a little while, you might want to go ptr sagemaker.update underscore packages, bracket, and press Shift Enter to update to the latest packages. Because if there's been a problem and I fix something for someone, the fix will be in there. So periodically do that once every couple of weeks or months or something, or before you're going on and doing something big. The other thing which you want to do is go into ptr sagemaker here, the directory which holds the code that runs everything, and go git pull from remote, and that'll update your commands in here. If you haven't done either of those two things for a while, it is a good idea to do it. But if you've just done it, don't worry about it. Just reminding you, just in case you've been using ptr sagemaker for a while, this part of the code may be updated quite frequently. So here we are. We've imported the SageMaker code. So now we are here and we're going to go and get our data from the archive. So we have a hat object here, and we want to get the photometry files because we don't need all the images, we just need the brightnesses of all the stars. So I'm going to start with all the PSX files. So if I just have PSX here, it'll just show us the PSX files. And down here I can change the number of rows per page and make it very easy. If you just select the longest number, click there, and in here go to download code for SageMaker. So you're not downloading code, it's a code that you can use to download these files into SageMaker. So click that, download that, and then we have to give it a folder name. So I'm going to go hat tester. Okay, copy the clipboard and press OK. Now we can paste that in here into this cell and then press Shift Enter, and then it will download. It won't take very long, but I'm going to pause the video so you don't have to watch that. Okay, so we've downloaded all of the PSX files into the directory hat test. There it is, hat tester. And now, so we've got all the photography files. Now we need just a single image file. So we'll press X here to unselect those, and then we'll get one image. We just need a single image. It doesn't really matter which one. The reason we're getting this is just to get some information that's stored with the image. So download one, download code to SageMaker, same thing, same directory name, hat tester, copy to clipboard. Now this one, I won't have to pause the video because it's just one file. It should download pretty quick. There we go. Okay, so now we have our photometry files, the measurements, and an image. Now there's actually 3 steps. First, we want to make this file that will tell ptEXOTIC what information we already know about the exoplanet itself. And that's actually the most involved bit and will take most of the time, but it's actually pretty straightforward. So what do we do? Well, we have this command ptr sagemaker dot run exotic on photo files. So this is a command. It will make this init file, it's called, with all what we know about the exoplanet. Then it will measure the exoplanet. That'll just start very quickly, and then it'll run exotic on the exoplanet. So after we finish filling out the information, it should just go straight into running exotic. So we need to give this command 4 different things. So the first one is the directory name, hat tester. Easy enough. Then we go and fish out our coordinates from before. Copy and paste. RA equals that, and then dec equals that. So this is the star in the image which has the exoplanet around it. And the last thing is you've got to tell it what type of file. So you have PSX files here. So you go photo format equals PSX. Okay, pretty exciting. In this directory, this star at that spot, using these files, measure and fit an exoplanet transit. So let's run it. And you get excited, and it says yay, but then you go, oh, I have to fill out stuff, which isn't quite as exciting. So if we make this work somehow. Sorry, I had to pause. I got lost there for a sec. So here's our window over here. Here's the information on the left. Obviously do this differently if I wasn't making a video. So we've got this boxes down here and we're going to fill it out. So we've got the NASA Exoplanet Archive thing for the star. And so it's asking us the orbital period. So that's a planetary parameter. That is P in days. And we basically just copy, paste, period days. Period uncertainty. Uncertainty is this plus or minus value, which is, how certain are we of this value. Published mid-transit time. So that's when, an occasion when the transit happened, basically, in the middle of it. So we put that in, and then you have the uncertainty again. Chuck that in. So this is basically copying it from here to here. The ratio of planets to solar radius, this looks different. So this star thing here is the RS. But here, it's pretty easy for me to type. 169, 0.0012. A on RS, so that's the one below it. 114, 0.23. Orbital inclination is this I for inclination. So 85.1, 1.5. If you don't know the eccentricity, 0 is fine. But here this star is eccentric, so it's 0.106. And the argument of periastron is this one, omega. 118, 8.0, and then plus or minus. Oh, it's not going to give a plus or minus. Okay, star effective temperature. So the star parameters are up here. So effective temperature is 5918 plus 121. I don't believe you can measure the effective temperature to better than a degree, so I don't bother with that. Metallicity is the where did it go? Metallicity, there we go. And that's quite an interesting number of significant figures to something you can't measure to any accuracy. So 0.017. No. If it just gives one value, then it's plus the same and minus the same. Log G, surface gravity. On the surface of the star, what's the gravity? What's the pressure? Plus uncertainty. And so yeah, this is sort of just straightforward. You're putting stuff in there, and as soon as you do that, when it goes red, that's when the next phase has started. So it's getting each of these files, which is corresponding to an image, and it's looking through them all, trying to pick a bunch of stars that are in every image, and to use them to make an exoplanet transit. It's basically the simple version, and it has finished that, so it jumps out of there pretty quick. Then it jumps into exotic, which is fitting the a red line, a fit to the data. So it'll take a while for this to actually figure out the fit. But if we go into hat tester, we'll see there's a whole bunch of stuff in here already. So this init.json file is a file which has been filled out by us answering all those questions. You'll notice there's lots of values we've plonked in. And there's some other values which it's got from the image itself. If we go into output cats, we'll see a few different files, but the V1 ptrEXOTIC file is what you want to have a look at. That is the file that is being used to look at the change of brightness over time of the exoplanet transit. So it has time, how bright it is, normalized to 1. So 1 is how bright it is on the flat bit outside the exoplanet transit. The error, and this is the air mass. How much air are you looking through? In output plots, if we look in the output plots directory, we will see, hopefully, yes, a bit of a transit. So problem with this dataset is we only caught parts of the dataset. We've got cloudy and wind patches. So, such is life. I'm just going to check on how this is going. So this is still going to take a little while. You can see numbers flinging around. Each of these parameters is being fit. It's trying to change the different values to try and make a fit an exoplanet what it expects an exoplanet transit to look like to this data. So it's still trundling along doing that. At some point it will finish. It's usually of the order of minutes, and it'll start outputting the results. So this is the final planetary parameters that it's fit, and it'll spit out a few final light curves here. So if we double click on final light curve, we'll see that magically, even though we've got patches in the data, it has been able to kind of identify where the transit was. And that's sort of due to the fact we gave it some good information on what it was looking for to begin with. And that was the point of filling out all of that information. You can see it fitting all the parameters. We can go into detail later about what this means, but each of these parameters, the midpoint transit, the size of the orbit compared to the size of the star, and the orbital size itself, how good the fits are. They should look like these curves like this, so it's been a very successful solution. And you can do this same process for any exoplanet transit you have. As a simpler version, a simpler light curve, a sample one here, WASP43b, voila. This is the test sample data. If you, which you don't even have to get the data, you can go ptr Sagemaker dot download WASP43 sample data and do that. It will make a directory called WASP sample, which already exists obviously, and put sort of stuff in there, and then you can run ptr Sagemaker dot test run exotic on WASP data. And here I've already filled out all of the stuff previously. I guess that's the other thing I want to say. If you fill out this form once and you find that it breaks somewhere in here, it won't ask you to do it again. It's not, so it'll only ask you to do it again if you remove that file. So that will stay there. So if you have to rerun it for some reason, or run a bit of it on its own, that file will still be there. So that's the introduction to ptrEXOTIC.